everyone, and welcome to today's STERIS Tech Talk on the future of sustainable EO, cycle calculation. STERIS Tech Talks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services that support these processes. My name is Sarah Krell, and I'll be the host for today's event. Our presenter today is Ken Gordon, a principal scientist at STERIS Applied Sterilization Technologies. Ken is a foundational hire to the EO Tech team and has developed and served in virtually every facet of the technical group's operations. His current role is centered around driving innovation for the EO Tech team and the EO industry at large, most notably with initiatives such as Sustainable EO Sterilization services. Ken has over 20 years of experience in medicine, contamination control, and ethylene oxide sterilization. All attendees are on mute for the presentation. However, we would like to encourage everyone to submit questions using the questions function and the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS AST YouTube channel. Please note that continuing education credits are not provided as part of this webinar. And now over to Ken to begin the presentation.
Thank you very much, Sarah. As Sarah mentioned, we're going to cover today the future of sustainable EO with a specific emphasis on cycle calculation. And for the agenda, of course, cycle calculation will be covered. We'll discuss methods and calculations. We'll cover a bit of a comparison between half cycle versus cycle calculation, and then some of the common questions we would get when qualifying with a method other than half cycle or topics such as requalification, product adoption, and process equivalence. So certainly we'll touch on those as well. So we've covered a number of EO topics over the last few weeks in this series of gas, specifically EO Tech Talks, and we'll continue to build on those today. The first one was on fundamentals of ethylene oxide and ethylene oxide sterilization. Last week's covered the sustainable EO. So just to put a brief refresher from last week's discussion, because it really does fold into today's topic, is sustainable EO. And what we have here is a pyramid presenting how to craft a sustainable EO process. And at the ground floor there, number one was PCD selection, where we're focusing on not over challenging the native product challenge. The second part of that, and the main focus of last week's discussion, was process development, where we talked about optimizing the various phases of your EO process. The one area that we did not go in depth on was process validation, and that's really the focus here, is what's the best process validation method to optimize your sterility assurance level and thus your EO exposure time, so you're not overkilling. And so that's what we're going to get into today. And another slide that I believe I had on the last presentation as a refresher, you've got a lot of approaches to validate a sterilization process. What we have here are 9 different methods that are covered in the main EO guidance, which is ISO 11135. And it's not important that you absorb every bit of this chart, but I do want you to understand that you have 2 basic ways to validate your process. On the left side here, you have a BI bioburden approach. On the right side, you have an overkill approach. And one thing you'll notice is one of those approaches, cycle calculation, is still overkill, but it actually uses the same methods that you could use for BI bioburden approach. You've just got a little bit of a different approach on what type of calculation you do based on the BI itself. So there is some overlap there in those methodologies. I mentioned there's two main approaches. We're not going to discuss BI bioburden approach in depth, mainly because overkill is what's used most often. And when we say overkill here, really what I want you guys to take home from that, using a full strength biological indicator, full strength meaning a 10 to the 6 population BI with the appropriate organism for your process. For EO, we use Bacillus atrophius. It's a very, very resistant spore former. And so as long as you're basing your validation on that 10 to the 6 Bacillus atrophius BI, you've got a very robust and conservative process. So to discuss a little further, we could really break this down into 3 main methods. You've got a half cycle overkill approach, a cycle calculation overkill approach, and BI bioburden, which is not overkill. It's a different method altogether. So they each have their pros and cons. For a half cycle method, you'll see at the bottom the green shaded areas that relates to simplicity or benefits. Of course, red would be more towards the negative side, kind of like a green, yellow, red stoplight kind of assessment here. So you'll see for half cycle, the complexity and level of micro monitoring is minimal with your half cycle. However, you do end up with excess sterility assurance level, and that's what SAL stands for, sterility assurance level, which in turn can lead to additional EO usage and higher residues and longer processing times. On the other end of the spectrum is BI bioburden, which is somewhat of an inverse to the half cycle as far as pros and cons. So you'll see, you actually trim down your SAL and EO usage, residues, and processing time, but you have increased validation complexity and cost, and more microbial monitoring required. And as I stated before, cycle calculation basically uses a lot of the same methods for BI bioburden, with the exception of use of a full strength BI. So what you get there is kind of a happy medium between both. And so I think oftentimes cycle calculation can provide the best of both worlds with regard to getting an optimal exposure time. And that's what really this whole discussion is about, is how can we trim down our EO exposure time in the most optimal method. So one of the things I mentioned in the prior slide was excess SAL, or excess sterility assurance level. Let's get into what that might mean. So let's start first with a discussion of what D value is, just as a refresher here. We know that microbial inactivation is logarithmic in nature. That's been known for almost 100 years, I think over 100 years. It was actually initially discovered by a lady named Harriet Chick over in England. But as long as your processing conditions are consistent, the time it takes to inactivate 90% of the population is going to be consistent. So if it takes, in this chart, what we have is a logarithmic representation here, where 10 to the 6th would be the same saying a million, 10 to the 5th would be the same saying 100,000. The time it might take to go from a 10 to the 6th to a 10 to the 5th population might be, and we'll just make up a time interval, 5 minutes. It would take 5 minutes to go then from 100,000 to 10,000, and another 5 minutes to go from 10,000 to 1,000, and so forth. And that consistency is really the foundation of our validation methodologies, all of them. From that, we can know how much time it takes to get down to that 10 to the minus 6, which is the standard metric for sterility assurance for medical devices. 10 to the minus 6 is the same as saying a 1 in a million chance of having a surviving microorganism. So generally up top here is measurable, and the farther down you go down here, the more difficult it is to measure these numbers, because after all, we're not going to test 1 million devices. That's just not a likely scenario for anyone. So that is D value. Sterility assurance level, as I mentioned, medical devices want you to be at 10 to the minus 6. So that's really what that's indicating, is the probability of a surviving microorganism. And another term you'll probably hear today is spore log reduction, or SLR. That simply references the reduction in population in logarithmic terms. So if we went from a overkill method, your best case scenario is an 8 spore log reduction in your half cycle. And the reason it's 8 and not 6, because people think, okay, when you show no growth at your half cycle exposure, that means 6 logs reduction. Well, that's not really accurate, because you're testing often at a minimum 10 samples. So you need to get beyond a 1 in 10 chance, would be 10 to the minus 1, to demonstrate all kill. And so that next step beyond 10 to the minus 1 or 1 in 10 is 10 to the minus 2. And so 10 to the 6 subtracted 10 to the minus 2, you get 8 logs of reduction. So that's where we get that 8 spore log reduction for a half cycle. And that's the absolute best case. Oftentimes you're well beyond that. When you multiply a half cycle log reduction by 2, you get 16 logs of reduction. Okay, and your starting point again is 10 to the 6. So therefore, you get 10 to the minus 10 as your best case scenario for sterility assurance level. Keeping in mind 10 to the minus 6 is the target that's required. So we're going 4 logs beyond what's required there. You know, and that's not overdoing it, but you should bear in mind that oftentimes half cycles are somewhat of a guess. And so you're often overestimating the amount of exposure needed. And so you're typically far exceeding that 10 to the minus 10 sterility assurance level. So that's just extra exposure that's not really needed and causing downstream consequences. Per cycle calculation, which again is another overkill method, you can calculate directly to a 12 log reduction. So from a cycle calculation, you will find out what the D value is and use that to calculate exactly how much exposure time it's going to take to get from 10 to the 6 to 10 to the minus 6. So that gives you a precise 10 to the minus 6 sterility assurance level based on an overkill process. So that's 10 to the minus 6 based on a 6 log BI that you're using to represent your process. All right, so the slight distinction here between BI bioburden is BI bioburden, you would base that calculation, that starting point on the bioburden of your native product. So if you had, say, a 10 to the 2 population, you would use that as your starting point instead of 10 to the 6. So that's the main difference. And so when I say cycle calculation is really probably an optimal fit between half cycle and BI bioburden, what I mean is you can probably save minutes to hours in your exposure time with a half cycle going to cycle calculation. But, you know, although cycle calculation exposure time would be longer than BI bioburden, you're really only maybe minutes longer, you know, when you consider most D values you'd come up with. So maybe 15 minutes, maybe 30 minutes longer. So you're not really saving all that much additional exposure time with a BI bioburden method over cycle calculation, but you have a lot of extra things that you have to do for BI bioburden that can make the process a bit more complex to qualify it. So now that we are all on board with saying cycle calculation is a great way to go for optimizing your exposure time, let's take a look at some of our options here. As I mentioned, step one is establishing the D value of that process. And although we have 4 different methods here that we can use to figure out that D value, and they come in 2 basic flavors. You have a direct enumeration or a fraction negative. Direct enumeration is basically a process where you take an actual enumeration of your BI at the start and at the end of your process and figure out directly how much bioburden is reduced. Fraction negative is a little different. You're not doing an enumeration or a population count on these BIs after processing. You're just testing all of the samples. And you'll hear me say replicates in this presentation. You'll test all the replicates. And what the fraction negative means that you're figuring out the fraction of those that are negative out of the total number of samples tested. And so you may have 6 out of 10 as just an example that are negative. And from that, you've got 3 different ways of determining D value from that. And there's pros and cons to each that I'll cover in our next slide. But if you want in-depth information on all of these methods, I would recommend you guys look into ISO 11138-7. All right, so when we're looking at the different fraction negative methods, you've got LHSK, which stands for Limited Holcomb-Spearman Carver. The procedures and requirements of that are very similar to Holcomb-Spearman Carver. The only difference is your sublethal exposures have evenly spaced time intervals for the limited Holcomb-Spearman Carver. And then you have Stumba-Murphy-Cochran. And when you do a comparison here, you've got 150 minimum recommended BIs, PCDs for SMC versus the HSK methods at 100. So that makes it seem like HSK doesn't require as much, but really I think that the pain factor here is the number of cycles you run. So with HSK methods, you need to run 5 different cycles to get your D value. With the Stumba-Murphy-Cochran, the SMCs, you only need 3. So that's one of the reasons we often recommend SMC over the other methods. The other being is that with SMC, with each sublethal run, you get a D value assessment. So you get it what the D value is for that run. With the Holcomb-Spearman Carver methods, you actually have to run all 5 different cycles before you get one answer on what D value is. So I really do recommend SMC. And sometimes a question you'll get is, isn't Holcomb-Spearman Carver the better method? That's often what's discussed first when they discuss fraction negative methods. What you have here is probably difficult for many, if not most, to see, and I don't want you to really focus too much on all of the minutia, but what this is an excerpt from the latest edition of Seymour Bloch's Disinfection, Sterilization, and Preservation. And what it is, it's a set of data from a lot of different types of BIs where they ran the exact same calculations on each one to determine D value for the Holcomb-Spearman Carver, actually limited Holcomb-Spearman Carver versus Stumba-Murphy-Cochran. And what you see on the far right side of this table is pretty much the D values are identical for almost each and every BI. So they really are comparable methods. So there is no necessary downside to using something other than limited Holcomb-Spearman Carver. So again, due to the accuracy of the D value calculations, either way, the comparable simplicity of the requirements and the ability to obtain a D value with each and every run, we do advocate the use of Stumba-Murphy-Cochran over the other cycle calculation options. And just a quick refresher here, because this is a lot of complexity here. Murphy-Cochrane is an overkill cycle calculation fraction negative approach. Okay, that's how all of this comes together. Now, getting into Murphy-Cochrane, how do we use it? Okay, this is the formula we use to calculate our d-values. And I know it can look intimidating, but it's actually not that complicated. And this formula, if it looks kind of familiar to some who are in the micro setting, this is based off most problem number theory, which is often used by micro labs to estimate microbial populations. And so what we have here in our formula, we have a T up top, that's our exposure time in minutes. We have the N sub zero, which is the initial number of organisms per replicate carrier unit. So that's just a long-winded way of saying what's the population of RBI starting. N sub U is what we are basically estimating as the endpoint based on that fraction negative number. And instead of a decimal or percentage, we take the natural log of that, so we can directly apply it to the starting population. So basically, we get, if we start at 10 to the 6th, and then the natural log of this fraction negative number gives you a 10 to the minus 2, this just enables you to take that spore log reduction at 10 to the 6 minus 10 to the minus 2, 6 minus 2, that'd be 8 logs of reduction. So that's all this is, and then you divide it by the time, that's the time taken to accomplish that. So it's really not that complex of a formula. It's just when you start using, I think, letters in your math, some people start to back out, but I don't want you guys to be scared of this. Okay, so here's a real world example. And what we have here is we exposed 50 BIs to a process, out of which 40 were negative for growth. And then our starting population was 2.4 times 10 to the 6, or written out long form, 2,400,000. When we plug all of that in, we get 7.03 logs of reduction. And then that, over that time frame, we get 7.3 minutes as our d-value. And it's as simple as that. Okay, so there are some other considerations here. So as we talk about the number of samples we place, there is a bit of conflicting instruction within some of the guidance documents on PCD placement. Willem 35 points towards distributing your BIs or PCDs throughout the load, whereas ISO 1138-7, which discusses these fraction negative methods a little further, they are generally recommending that your PCDs are statistical equivalents. And what that means is generally they talk about placing them all together. I think it's important for one to consider temperature and humidity distribution throughout your load. If your conditions are fairly even throughout your load, I would say you're probably fairly safe in distributing your PCDs throughout the load. If you got a lot of variance, you're really going to want to ensure you're challenging any worst case areas, and that's generally a temperature consideration. Where is your temperature coldest? That's going to be addressed. So this kind of conflicting information in the next revision 135, which is just now getting underway. But generally, we recommend distributing throughout, at least to start. Another thing to consider is when we're using our dwell time to determine D values, we want to make sure we go beyond just the default dwell time listed in your run records. You want to incorporate what we call our equivalent exposure time. And that's something you can estimate based on just taking the injection time for EO, dividing by 2, the nitrogen overpressure, if you have one, and the evacuation time immediately after exposure, dividing that by 2. And what that gives you is a rough approximation of additional lethality outside of the specific exposure phase. And what this does is it gives you a more conservative D value output, so that you can make sure you continue to have a conservative estimation on what you need for your overall exposure time. So let's take a look at what the equivalent D value might look like in calculation in a real world example here. So if we only consider dwell time for this process, it would just be 30 minutes. But when you factor in the EO injection time of 20 minutes, and again, we're going to divide that by 2, the nitrogen overpressure, which is 4 minutes, you take that in full, and then the EO removal time of 14 minutes, which you would divide by 2, you actually end up with 21 additional minutes of exposure time for a total of 51. And that's going to give you a very different answer on what the overall D value of your process is. And again, we highly recommend using equivalent exposure time. The exception there would be is if you have something close to a beer type chamber that can deliver a very quick injection and very quick evacuation. But for most of us, we're not validating a process on a very small beer style chamber. We're installing on larger chambers that hold multiple pallets. And so our injection times, evacuation times are often in 5 or 10s of minutes, and that does add to overall exposure. We want to make sure we consider that. All right, so how can that impact the process? So from the worked example I've used throughout, we've discussed the dwell time is actually 30 minutes, equivalent time is 51 minutes. We have a starting BI population 2.4 to 10 to the 6. And factoring all that in, if we only use that 30-minute dwell time, we might say that, hey, we have a D value of 4.3. When we factor in that equivalent exposure time, we actually show a D value of 7.3. And the difference in these two lines here, and what I should point out, is this red dotted line here that you see, that's our target. That's the 10 to the 6th. So the actual dwell time you would end up with total would be 52 minutes if we only use dwell time for our D value calculation, but 88 minutes if we factor in the more conservative equivalent exposure time. And again, this is what we recommend because you want to make sure you maintain the conservative aspects of this process. If we want to compare this to, excuse me, a half cycle method, that exposure time would keep going further out and all the way out to here from a time perspective. So if we looked at the 9 logs of reduction and multiplied that and got down to the 10 to the minus 12, again, that's minimum. You can see the difference in potential exposure times. So a cycle calculation, we know precisely 88 minutes is what we need for dwell time. If we do a half cycle method, 132 minutes would be the absolute minimum we would come up with under these same conditions. And again, all of this is compared to the native product bioburden, and this is probably an exaggeration of the challenge level of bioburden because it would not be as resistant as your BI typically, but certainly it's going to be lower here. All right, so that's just showing the comparison there, how you're far beyond that. Okay, there are other considerations beyond just D value, okay? So for Stone Murphy Cochrane, you're going to run 3 sublethals, and you're going to assess D value for each and every of those sublethal runs. The D value used for your spore log calculations is an average of those 3 sublethal runs. When we talk about microbiological performance qualification and physical performance qualification, that's listed here as MPQ and PPQ. Those are the same considerations as your half cycle methods. And so you would still reference 1 Lum 35 in the same areas to determine, sensors for temperature and humidity monitoring and things like that. Your sublethals that you're running, those are certainly suitable as long as you're using a production chamber for your MPQ and PPQ work. Generally, we'd recommend to perform your sublethals at minimum tolerances that impact lethal conditions, so minimum spec temperature, humidity, and EO concentration. Since we are recommending combining both MPQ and PPQ data from these sublethals, you would need to run at least one full routine exposure process to complete your PPQ requirement. And again, that's the same as a half cycle method, so there's nothing different here. We just want to point that out. And again, you're just taking the average of those 3 sublethal runs, multiplying by 12, and that gets your minimum exposure time you need. More often than not, people will end up going beyond 12 logs of reduction just to add a bit of safety padding. You don't want to overdo that because then you're negating the value of your cycle calculation, but it certainly can make sense to consider adding a few extra logs of reduction just to future-proof your process a bit. All right, when we get to requalification, you've got the same, you're going to reference 11135, and it's going to give broad guidance here. And it's mostly the same as what you do for half cycles. You're going to do an annual review every year. That's almost a paper review. You're going to look at everything that might have impacted your process or your manufacturing process. The difference is instead of a half cycle to requalify your process, typically you're going to run either the same type of sublethal, Somerville Cochrane cycle you ran, or you can do a kill time cycle, which the formula is here. A log of your BI population plus 4 times the calculated D value. And so for this example, that would come out to 77 minutes and 51 seconds. So you've got a couple of ways of going about it here. And of course, you're going to look over your parameters, your temperature and humidity loggers, and also do that to requalify the physical PQ side of things. So how do we adopt something in? Well, again, it's going to be the same as your half cycle approach. You're going to assess the new product against your existing master PCD. And then if the assessment requires any MPQ data to support it, you would just run a sublethal fractional to establish the relative resistance of the new candidate product to your current challenge device that you qualified your process around. And then, of course, if the candidate product's less of a challenge than the master product PCD, then it can be adopted in. So again, no difference at all here in half cycles versus a cycle calculation for product adoption. And then the same goes for equivalence, really. You evaluate the IQ, OQ of the candidate equipment you want to qualify in. You would identify and document areas of equivalence and areas that are not of equivalent. And more often than not, you end up running a microbiological performance qualification cycle to confirm lethality, and oftentimes a physical PQ at the same time, just to demonstrate that your temperature and humidity is within the initial validated range. But again, this is exactly the same as what you would do for a half cycle, except instead of a half, you'd run a sublethal or the kill cycle option we mentioned on the prior slide. So to summarize here, I want to just kind of give you a broader picture here. Cycle calculation overkill is a more quantitative means of validation, meaning when I say quantitative, I mean we're actually getting a numerical assessment of the lethality in the form of a D value. Half cycle overkill it's still somewhat quantitative. I would call it semi-quantitative, but it's more of a qualitative. You're really just kind of guessing the kinetics of your process itself, and that will really help you diagnose potentially future issues that may arise. As I mentioned, you're reducing the level of additional overkill that you would experience with a half cycle method. And then if there's ever any doubt in your exposure time, you can always confirm with running an all-kill cycle. And when you look at the number of cycles required, comparing Stomach-Murphy-Cochrane to half cycle, it's really the same number. It's either 3 sublethals for SMC or 3 half cycles for a half cycle method. So you're not really having to run additional cycles to qualify your process. So it's really much on par in that respect. And I should also say, cycle calculation really complements parametric release well, because you're really trimming everything down to its essence and getting a really good understanding. Adding the parametric release in there really gives you further understanding of the conditions in the chamber. All right, so that is a general overview of cycle calculation, which we recommend if you're wanting to optimize your exposure phase.
Thanks again for joining us today. This concludes the webinar.